up, I'll mention him as well. So please proceed, Brock. Thank you.
Great, thank you, Tom. All right, we don't need to go there. So when we look at our onshore production facilities, one of the bigger challenges we face in our maintenance and reliability programs is the soil side corrosion of our above ground storage tanks. This area is very difficult to access, and as a result, it's difficult to monitor and implement corrosion mitigation systems for the underside of our tanks. When we look at the systems that we typically use today, there's a few ones that you will see common: cathodic protection, vapor corrosion inhibitors, and different passive barrier systems that could be traditional coating systems as well. And when we look at our field experience here, when we talk about cathodic protection and vapor corrosion inhibitors, these systems require pretty extensive design, and they still often don't apply across the entire underside of the tank, which allows corrosion to continue to occur. And they also require extensive maintenance and monitoring to maintain their effectiveness over time. When we look at a lot of the other traditional barrier systems, like traditional coatings, these can't handle the construction process, whether that's the physical damage during installation or the heat input during the welding process. Both of these create significant coating holidays, and you get lots of bare spots, and then we get localized corrosion on the underside of our tanks, which we can all agree is not good. So there's a pretty big need and driver for a easier to install, easier to maintain, and manage corrosion mitigation tool for the underside of our storage tanks. And to do this, we looked at a ceramic conversion system, that forms an alloy layer on the steel. This alloy layer acts as your corrosion barrier to prevent corrosion. It also forms a ceramic layer over that. That gives us a little bit of additional durability, and it also maintains that alloy layer over time. And so this study looked at how we can evaluate whether or not the heat process during welding impacted this coating system's ability to form that corrosion barrier, and if it changed any components or chemistry aspects to that coating system. And in order to do that, we worked with our third-party lab to develop and implement various lab testings to study, which Amal is going to share for us.
Thank you, Brock.
Thank you, Brock. So one thing I would like to mention that Brock maybe forgot, that this coating has been tested before for several applications and proved to be really effective. But the only thing we didn't know is what's the effect of welding in this coating performance. We designed the test protocol to understand clearly what's going on during the welding and what's the effect of the welding in the microstructure of the steel and the morphology of the coating itself. Then we took it the second stage. We tried to use electrochemistry, which is for the first time we're using it, to see what's the effect of this alloying layer formed during the welding and non-welding process comparatively. And the last thing, after we understand the system, we went and we evaluate its performance under long-term immersion and cycling process, which simulate actual application in the field. I'm gonna give you the result for each part, and then Benjamin from Chevron, the project of leader for this, he's gonna wrap up the conclusion for you. First of all, I would like to tell you that we have used test panels which were cut from an actual plate, an actual tank plate, which were brought from the field, and they were welded. But before welding, of course, they applied the coating to the other side, which is the side which is gonna face the soil of the tank. And they cut it, the actual, I think, plate were about 120 inch, and it is like 60 inch, and the overlap area of the welding was 8 inches. For easy of transportation, we got 60 by 60 inches, I think, and we cut the test panel from the actual application in the field because we want to see what's happening in the field. We don't want to have it under ideal conditions. So, oh, sorry. Shall I go back? Okay.
Green.
The green. This is the back side of the panel that is gonna face the internal of the tank, whereby here is the coated that is gonna face the soil side of the tank. As received panel with the coating, we find that on the welded area, there is discoloration, okay? And we said, okay, fine. Then we start cutting the panels for the test, for the immersion test, for the electrochemistry, and for the aging. And we have observed that there is also some cracking and some despondent of a little bit despondent after we cut the panels. We selected panels that did not have any of these because we created our own despondent or our own damages to it. The first thing I said, we wanted to know what's the effect of welding into the steel itself, the morphology of the steel. We identify the heat affected zone because it has different color and pattern. And this is, oh my God, I keep on forgetting. The green. This is the heat affected zone, which has different color. And this is the welded metal, and here the base metal. And this is under 10x. So when we looked further under the microscope, under 100 magnification, by the way, I can see, I'm gonna look at here. Under 100 magnification, we found that the microstructure in each area is totally different and indicate that the weld area has been exposed to temperature up to 1500 C, whereby the heat affected zone was about 900 C, and the base metal just adjacent to that was about almost above 600 C. We did this on non-coated metal because we assumed that this is gonna happen the same thing if it's the other side was coated. Then we said, okay, we identified the heat affected zone, and then we went to the back side where is the coating, and we tried to look into the structure of the coating. What happened to the three different areas identified by XRD data? And we looked at the abundance of course, it's a complex structure. Yeah. It's a complex structure, so we would like to look at the abundance and occurrence of different component into the coating. What we found that for the blue one is the non-welded, and the orange one is the welded sample. So we took samples from welded, and we took sample from non-welded at all, just a panel, coated, did not have any heat effect. What we found that the heat of the welding can decrease the abundance of the crystalline product and will increase the abundance of the amorphous product. So it has some changes into the morphology of the coating. We took chips from the non-welded sample, and we took chips from the welded sample, and then we looked at the ACM analysis with DSC. And what we found, the same thing. Where there is no welding, we have a crystalline. When there is welding, we have more of amorphous, as indicated by phosphorus, magnesium, calcium decrease in the welded one, whereby aluminum, silicate increase in the welded one, the unwelded welded. We removed the coating, and we tried to look at the layer, the first layer formed. What we found, the same thing. It is amorphous versus crystalline one. Now we know there is an effect. Now we know that if you do welding, you're gonna have an affected zone, you're gonna change the morphology of the coating, and you're gonna change of microstructure of the base metal. For the first time, I think in my lab also, I've used the electrochemistry to evaluate the characteristic of this layer, to evaluate. Due to the nature of this coating is a little bit porous, we could do that. We designed a special cell to determine the effect on the weld exactly versus the effect of the non-welded. I'm not going to go into details into the electrochemistry because all of you know, and we mentioned it in detail in our paper, but I'm going to show you what we have observed from this testing. The first thing we did, we compared the open circuit potential of welded and unwelded bare metal without any coating versus welding and unwelded. Why is wrong with me? Okay. The welded of the coating one. The top lines, it shows the welded and coated and unwelded and coated, with the bottom ones, it shows that the bare steel metal. And as you can see, the decrease of potential of the active metal indicate that the top ones has a passive layer, or it is it has something protection for it. The only thing we also observed here that the open circuit potential did not really affect welded or non-welded. We didn't see any of that. The second step, we went to linear polarization. And in the linear polarization, of the welded, non-welded sample, and this is the welded coated sample, non-welded coated sample versus the bare steel. This is indicated it's an active metal, whereby the above two indicate there is passivation. However, the higher the polarization potential, the lower the corrosion rate. As we can see here, in the initial 15 days, the polarization potential for the welded one is lower, means its corrosion rate is higher, versus the non-welded one. However, the most important thing we observe here is after 2 weeks, both of them start acting the same thing. Well, I'm not going to comment. Benjamin will comment to that. But this indicates that this is the top layer has provided what is missing from the first layer into the component of that. The second one, we went into the cycling polarization potential, and the same thing, the one on the left is related to non-welded versus the red one is welded, and here is an active non-coated welded and non-welded. I'm going to start with this one. It's a typical no passivation, no layer, and an active metal. The welded and non-welded perform the same, whereby here, if we look at this polarization, and you can see that as we increase, the eye pitting here increase, which is usually happen for passive layer. However, if you release that and it goes back into this loop, hysteresis loop, and it is cut slightly under the open circuit potential, and this is a characteristic that this layer is susceptible to pitting and crevice. However, for the corroded, the welded ones and coated, we didn't get this increase, and this shape is different, and this indicates that there is a partial of this passivation. There is the passive layer, or the first layer has been compromised. This is all what I want to tell you, although from here, you can also determine the corrosion rate, and we have observed that the welded one, coated, has tenfold higher than the non-welded coated sample, which is in agreement with our linear polarization test before. Now we know there is a layer, there is a passive layer. However, we have understood from the two parts that this layer, the first layer, is susceptible to any pitting or any under crevice corrosion. However, we have found that linear polarization, that after 2 weeks, it takes some time for it to come back to normal. So we know there is a problem. We know there is a change in the morphology of the coating. We wanted to know if this happened, and we used it in the field, how this coating is going to perform. The two tests we have conducted that simulate actual field experience is the immersion test, and we did do panels welded, coated, and panels welded, panel coated, non-welded. We conducted the tests for 40 degrees C according to the ISO 2812-2, and we have removed sample after 1 to 3 months, okay? What we have done, we created artificial scribe on the weld, where there is the weld, and the same thing on the non-welded sample. The result we have observed after 3 months exactly, there is no blistering, cracking, swelling, rusting, under creep. There is no under creep or any sign of coating degradation, okay? The only thing we observed here, for the coated welded one, we started with a lower pull-off values than with the coated non-welded. However, within time, we found that there is an improve in the coating, in the pull-off value, and on the mode of failure. Initially, with no welding, the mode of failure was to the steel or to the alloying passive layer. However, after we immersion testing, the pull-off adhesion strength has increased, and the mode of failure was cohesive within the ceramic layer. The second test we decided to do is an aging resistant test. We want to age the sample. We conducted according to the ISO 12944-9. However, we modify it in order to simulate condition in the field. So we did like 4 cycles. The first cycle was for 1 week exposure to condensation, followed by 1 week exposure to the salt fog, followed by 1 week of dry condition at room temperature. And after each cycle, we have taken sample and we evaluate the performance of the coating. We have also observed there is no rusting, there is no blistering, there is no change of color, there is any sign of degradation for welded coated and non-welded coated. The only thing we can do here is to evaluate the coating according to pull-off adhesion strength. And here, this figure show you the pre-test pull-off adhesion test of the orange, of the welded, and the blue of the non-welded. So as you can see that there is an increase in the pull-off adhesion, the same thing as we observed in the immersion testing, and the mode of failure also a change. However, for the non-welded one, it stayed almost constant. The other important things, because we made artificial scribe on the weld itself, it might happen during installation, during anything, you might damage or crack the top layer. We found that, of course, the blue one is the under creep non-welded, where the orange one is the under creep welded. So as you can see, after the third cycle, we start seeing the same performance, whereby for the 3 and 6, always the non-welded has a better performance than the welded. Okay, I am gonna leave the floor for Dr. Benjamin to wrap up the study.
Sure. I'm Benjamin Challoner-Gill. I work for Chevron. I work in our materials technology team.
Okay, what you have here is your laser pointer,
that's good.
advance, and go backwards.
Okay.
And get near the microphone.
Sure. So just to conclude, I'll let you guys read the conclusions. Just I want to talk through a little bit here. One is that, you know, the system we're looking at here is it's a chemical conversion system. And we're understanding the chemistry that's going on and what happens as a function of time. And that's what you're seeing a lot in the data through the different work that Amal did in managing and learning what the system can do, how it acts, and what it's going to do. One of the things that you find out with this is that it is one that it fixes itself, where somebody would call it a self-healing system, differently from you think of a polymeric self-healing system, but you wouldn't be able to see the results of the data coalesce after a period of time that still give you the corrosion protection. So it's undermined here that even though we do see changes in chemistry from the heat of the weld, you still get a system which will give you corrosion protection. And that's the takeaway for us as we did the study here.
Is that it?
That's it.
Okay.
So we have time for short questions.
Any question?
No? So it's what's the final decision? You gonna do it?
So we're